Hi there. So in this video, we're going to be looking at two sections. The first half of the video will be on section 2.3, composition of functions, and then the last half of the video will be on section 2.4, which will look at symmetry and odd and even functions. All right, so here at the top, we are looking at composition of functions, and there are two notations for composition of functions. The first notation over here on the left, I use less often. I actually, in fact, I rarely use the notation over here on the left. But if you're working in MyLab Math or see it in a textbook, it's important to know the difference between the two. This is an open circle here, so this is not read as fog. This is f followed by g of x. And again, that's equivalent to f of g of x. So without that parenthesis, without that circle there, remember that means f followed by g of x. Over here on the right, then f parentheses g parentheses x, close both parentheses. This is read as f of g of x. To find the domain of these um, composition of functions, it will always be the intersection. And when I say the word intersection, again, I'm just like the last section, I'm talking about where they overlap. So it's the overlap of your interior function with your answer, your resulting function. With these composition of functions, you're always going to be working from the inside out, meaning when I say inside out, then I'm working with g of x first, and then whatever answer I get, I'm going to plug that into f. Okay, so that's what I mean by working from the inside out. All right, so I'm going to start you here with example one with a common real life example of functions that we could think about in terms of these composition of functions. While probably, admittedly, we don't think about them in this manner, um, I think this will be a good way to get you used to the notation of composition of functions, something that you already have a working knowledge with. All right, so here in example one, it says given that f of x equals 0.75x, and that represents how to find the price of a TV after a 25% discount is applied. Okay, so you go to the store, maybe you go to Target, Walmart, Best Buy, wherever you go, and there's offering 25% off these TVs. Well, then that means you're going to pay 75% of that price. So that's where this formula is coming in here, 0.75 times the price of the TV. And that will be how much you'd pay. Well, we all know that once you go to buy something, you also have to pay tax. So a g of x function is established here as 1.07x, and it represents how you'd find the price of your TV after tax is added in. So what it wants us to do is use these two functions and our new notation up above here to find the total price of a $600 TV that's being discounted by 25%. So think about it. Whenever you get up to the cash register, they're going to take that $600 TV. Are they going to calculate tax first, or are they going to take the discount off first? And hopefully you agree. They're going to take the discount first. So f of x is going to be what is going to happen first, and then after you figure out what your discount is, you're going to pay tax on the discount. Okay, so here's our g followed by f of x. We're going to work from the inside out. I'm going to evaluate f of x first. Now, x is the price of our TV. It's $600. So I'm going to find g of f of 600. Okay, so just like I mentioned to you up above, you're working from the inside out. So the very first thing I'm going to find is f of 600. So I'm going to go to my f function. I'm just going to come over here and remind you, f of x is equal to 0.75x. I'm finding f of 600. So everywhere I see an x, I'm going to plug in 600. Pop that in my calculator. That should put you at 450. Yeah, 450. All right, so now I know then that f of 600 is 450. So after you have, so essentially, after we've taken the discount off, the $600 TV is now $450, and our out the door price will be after we pay tax on it. So that's what the g function is going to get for us. That g of 450 now says go to your g function. Everywhere you see an x, you're going to plug in 450. So 1.07 times 450 should land you at, out the door, $481.50. Final answer. Okay, so hopefully that gives you, like I said, a nice application and something that you can relate to in terms of these composition of functions. All right, we'll scoot on down here to example 2. In example 2, I'm giving you an f function and a g function, and I am asking you to find f of g of -5. And just like I talked to you in the last section, if you're plugging in a letter, final answer is going to be a letter. If you're plugging in a number, final answer is going to be a number. So in example 1, we were plugging in a number and we got an answer of a number. Here in example 2, we're plugging in another number, so our final answer should be a number. All right, so this time I'm f of g of -5, working from the inside out. So that tells me then first thing I'm going to find is I'm going to plug -5 into my g function. So go to my g function. Everywhere I see an x, plug in -5. So that'll give me -10 plus 8. So that should land you at -2. All right, so we just found then that g of -5 is -2. So now this says go to your f function. Everywhere you see an x, plug in -2. So f of -2. -2 squared will get you a +4. 2 negatives side by side will also get you a positive. 4 plus 2 is 6. Final answer. So f of -2 is 6. That's our final answer. All right, we'll move on down then to example 3. In example 3, I've got an f of x and a g of x function. This time I'm just asking you to find g of f of x. So I'm not asking you to plug in a number, so our final answer here is still going to be in terms of an expression. All right, so let's work from the inside out. F of x is x cubed minus 5. So I'm working from the inside out. F of x, I'm going to replace f of x with what I know f of x is. F of x is x cubed minus 5. So I'm plugging that in there. Now this says go to your g function. Everywhere you see an x, plug in x cubed minus 5. So I have x cubed minus 5 squared minus x cubed minus 5. Parentheses are vital in this problem, and I always recommend if you're substituting, use parentheses. All right, so for that first one, got to have it so that you can write that twice so you'll be able to FOIL it. And that second one, that's a minus sign, so that's really a -1 that's going to get distributed back there, so that will be minus x cubed. Negative times negative will give me a +5. All right, so now we got a FOIL up here at the front, so multiplier first, x cubed times x cubed. When you multiply, add those exponents, so x to the 6th. Outside, x cubed times -5 minus 5x cubed. Inside, another one of those. Last, -5 times -5. Bring everything else down. Last final answer will be to combine like terms, so I have x to the 6th, x cubed. I got -5, -5, and -1, so minus 11 x cubed. Numbers 25 and 5 combined to give me 30. There is my g of f of x. Final answer. All right, so now here in letter B, it says find the domain of g of f of x. So again, so I'll remind you, back up here at the top, it said that our domain for these were going to be the intersection or the overlap of our interior function with our answer. So our interior function is my f of x. So looking up here at my f of x function, asking myself those same 3 questions. Do you have a letter in the denominator? Nope. You got an even root? Definitely, I don't have a square root here, so nope, I don't have that either. So answered no to both of those questions. Negative infinity to positive infinity. And then I need the domain of my answer that I just got. And so when I'm talking about the answer, I'm talking about this guy right here. So looking at that answer there, do you have a letter in the denominator? Nope. Do you have an even root? No to that as well. You answered no to both those questions, so you got negative infinity to positive infinity. I need to overlap those two. We saw in a previous video, if you overlap negative infinity to positive infinity with itself, that's going to land you at negative infinity to positive infinity. Final answer. Okay. Let's flip it on over. I'm going to do example 4 and 5 with you and let you try example 6 on your own. All right, so here in example 4, I'm giving you an f of x and a g of x function. Over here on the left, I want to find f of g of x. All right, working from the inside out. So f of my g of x, x minus 1. So now this says go to my f function. Everywhere I see an x, I'm going to plug in x minus 1. So I have 2 parentheses x minus 1 squared minus 3 parentheses x minus 1. All right, so now I'm going to take that don't know why this pencil all of a sudden has come up. Take that x minus 1 and write it twice so I can FOIL it. I'm going to take that negative 3 and distribute it through, so I have minus 3x plus 3. Alright, so now let's FOIL. First, that will give me x squared minus 1x plus 1. I'll burn another step. I'll combine like terms. Distribute. Try again. Minus plus 2. Alright, last step. Combine like terms. About that. So that gives me then 2x squared minus 7x plus 5. That would be my final answer. That would be my f of g of x. Alright, plugging in a variable. Final answer is in terms of variables. Over here on the right, I'm plugging in a number, so final answer is going to be a number. Working from the inside out, this says go to your f function. Everywhere you see an x, you're going to plug in negative 2. So, going to my f function, so I'm just going to come over here and kind of write this out to the side. So f of negative 2. Everywhere I see an x, I'm plugging in negative 2. Alright, so you could put that in your calculator all at one time. I'll just show a little bit of work. Order of operations, say I got to square that first, so that'd be 4. Negative times negative would be a positive 6. 8 plus 6 will get you 14. So f of negative 2 just turned into 14. So final answer will be to find f of 14. So that says again, go to your f function. Everywhere you see an x, plug in 14. So that would be 2 times 14 squared minus 3 times 14. And I'm just going to say you put that in your calculator all at one time and you should land at 350 final answer. Okay. Alright, I'm going to move on down then to example 5. In example 5, you are given an f of x and a g of x function, and I'm asking you to find both f of g of x as well as g of f of x. So whenever we're working through these, and we're also going to be finding their domain. So I'm going to do, like I said, I'm going to do example 5 here with you. Example 6 is very similar to this exact same problem, so I'm going to let you try example 6 on your own and check yourself by the solution key. Alright, so now since we're going to be having to find the domain, and in both of these, one of them is the both of them are going to be the interior function at one point or another. I'm going to go ahead straight away for here from the top, and let's go ahead and get the domain of f of x and the domain of g of x, because we'll need it later on. Okay, so looking at my f of x function, first question, do you have a letter in the denominator? Yes, you do. So you're going to set that denominator 1 minus 7x not equal to 0, solve for x. So I got running a little low on room over here, but let's see what I can do here. Subtract 1 on both sides. So I've got negative 7x cannot equal negative 1. Divide by negative 7. So we find then for f of x, x cannot equal a positive 1/7 because you got a negative divided by a negative. Over here on the right for your g function, do you have a letter in the denominator? Yes, you do. It's only one term there, so it cannot equal 0. Okay, so right now then you've got your domain for your f and your g. So remember, we'll be overlapping that interior function with the answer that we get. Alright, so let's come down then and let's do the first part here. In the first part, I want to find f of g of x. So I'm going to work from the inside out. F of my g of x is 1 over x. So now this says go to my f function. Everywhere I see an x, I'm going to plug in 1 over x. So that leaves me then with 5 over 1 minus 7, and then I'm replacing that x down there with 1 over x. Because again, that says go to your f function. Everywhere you see an x, plug in 1 over x. So here was my f function. So that x was replaced with 1 over x. Alright, so now let's clean this up. So up top, I'm left with still the 5. 1 minus, now on the bottom, you can think of this as 7 over 1, so we multiply straight across, so that would be minus 7 over x. Now, it's not proper nor legal to leave a fraction within a fraction, so what you do then is you multiply by the common denominator. So the common denominator would be you would look for the common denominator in the denominator. So here's my denominator, common denominator, the only denominator in the denominator is x. So I'm going to multiply everything by x. And so what that allows me to do then is up top, x times 5, 5x. On the bottom, x times 1, just x. And you can write a 1x if you like. Now for that last term, that x in the numerator here with the x in the denominator cancel out and just leave you with the minus 7. Okay, so that, I'm going to box that in. That is our f of g of x. Okay, so now to figure out our domain, we need the domain of our interior function or the domain of our answer. So the domain of our interior function, so the interior function this time, when we started with, that was our g. And again, we've already established what that one is. X cannot equal 0. Then we need the domain of our answer. Okay, so that's the answer that we just got. Okay, so that's looking at this guy right here. The answer that we just got, do you have a letter in the denominator? Yes, you do. So that denominator then cannot equal 0. Solve for x, so we'll pull that 7 over. So x cannot equal 7. So now what needs to happen is I need to overlap these two right here. All right, so I'm going to do like I did before. I'm going to draw you a picture. All right, here's the standard number line. First one says I can equal anything but 0. So here's my 0. And I'm shading in both directions. Second one says I can equal anything but 7. So here's my 7. They know that, your number lines don't have to be to scale. And I guess technically you don't have to have a number line. I think they're helpful though. Anywhere the green and the blue are on top of one another is where they overlap, and essentially they're on top of each other everywhere, except we just got to pause at the places where you're undefined. So overall domain then, negative infinity to 0. Then we're going to go from 0 to, hopefully you agree, and I stop at the 7. And then go from 7 to positive infinity. That would be my overall final domain. Okay. All right, let's come on down then to the second part here. We are using the exact same two functions. We are just switching what my interior function is. This time I want to find g of f of x. So starting from the inside out, here's my f of x. So I want to find g of, my f of x is the 5 over 1 minus 7x. So now this says go to your g function. Everywhere you see an x, you're going to plug in that 5 over 1 minus 7x. So my g function, 1 over, in place of that x, I'm going to put 5 over 1 minus 7x. Just like I demonstrated for you in the last problem, I can't leave a fraction within a fraction, so we multiply by your common denominator, which essentially is the denominator in the denominator. So in our case here, that'd be 1 minus 7x. So up top, 1 minus 7x times 1, that's still 1 minus 7x. And then on the bottom, the 1 minus 7x's cancel out and just leaves you with 5. Now we are good to go. We've got it all cleaned up. That is your g of f of x. Okay. Now let's move on to our domain. Okay, for our domain, we need the domain of our interior function. So this time, the interior function, what we started with was our f. So looking back at the top, our f domain, x could not equal 1/7. Then we need the domain of the answer that we just got. Okay, so that's this guy right here. Trying to find the answer there. Trying to find the domain of that answer. Ask yourself the questions. Do you have a letter in the denominator? No, you don't. Do you have an even root? You don't have that either. Remember, even roots mean you got to have a square root, a fourth root. You've got to have that symbol, okay? You don't have that. So your answer no to both of those questions So you got negative infinity to positive infinity. All right, so now let's get you a picture here. You got your full number line. All right, so f says you can equal anything but 1/7. So I'll just pop a 1/7 here. I can equal anything but that. And g says you can equal everything. And everywhere that red and blue are on top of each other is where they overlap. And so hopefully you agree they're overlapping everywhere except we've got to excuse me, pause where they where it makes the one where the 1/7 makes the denominator equal to 0. So overall domain then, negative infinity to 1/7, and then 1/7 to infinity. All right, I'm going to let you go on and pause the video and try example 6 on your own. And then we will come on over to section 2.4. In section 2.4, we're looking at symmetry as well as odd and even functions. So symmetry is pretty straightforward. There are tests for symmetry, but by and large, most folks follow symmetry by being able to look graphically at the picture. So looking at our so anyway, I can if we need to talk about utilizing the tests, we can. So, but by and large, I'm going to look at symmetry by looking at the picture. Okay, so here's what I mean by that. In order to be symmetric to the x-axis, what that means then is that if you're looking at a graph, if a graph is symmetric to the x-axis, then what that means then is that if I were to fold it across the x-axis, that graph would be on top of itself. And hopefully you would agree here. If we were to fold it across the x-axis, the top part would be on the bottom part, or if you folded it the other way, the bottom would be on top, would be on the place of the top. Okay, so that's what it means to be symmetric to the x-axis. You can fold it over the x-axis and it's on top of itself. There is an algebraic test. You replace y with negative y, and if you get the same equation after you clean it up, that's another way to see that it's symmetric to the x-axis. All right, to be symmetric to the y-axis, same thing. I need to be able to take my graph and fold it over the y-axis, and it would be on top of itself. So I'll use an absolute value curve here for us. Okay. Right, and if I were to fold it over that y-axis, the left would be on the right, or vice versa, the right would be on the left. Symmetric to the origin means that you have to get to flip, and I'll go back and say the algebraic test for being symmetric to the x-axis, you replace x with negative x, clean it up. If you get the same equation, then yes, it's symmetric to the x-axis. To be symmetric to the origin, you have to be able to flip it over both the x-axis and the y-axis. Order doesn't matter, so you can flip it over x then y, or vice versa, y then x, but you still need to be able to, then the graph would be on top of itself. I will use the cubic function here for this one. So you got to think about, if I flipped it over x, then this bottom portion here would be up here at the top. And then if I flipped it over y, it would fold over and be all on top of that piece right there, okay? Or you could, like I said before, you can flip it over y and then flip it over x, okay? Algebraic test there, you would replace x and y with their negative counterparts and then clean it up. If you got the same equation, it would be symmetric to the origin. I'm not going to go over that testing here in this set of notes. I found that actually it's usually more confusing than not, but if you're not getting it graphically from the picture, come see me or reach out and I'll be happy to go over those tests with you. All right, so down below here in example 1, 2, and 3, it just is asking us to determine what type of symmetry we have. And it should be noted, I didn't say this already, it should be noted that it is possible for a graph to have more than one type of symmetry or not to have any symmetry at all. Okay, so just so you're aware of that. The examples that I gave you up above only have one type of symmetry, but like I said, it's possible to have more than one, and I'll illustrate that down here below in these examples. And I will also and it's also possible not to have any symmetry. Okay, all right, so what you would do with these problems then is if your equation is not already solved for y, you would solve for y and then you would pop it into y equals and graph it. So in that first one, if we were to graph it, you would find that the graph itself would look something like this. Y equals 1 over x. And I encourage you, pause the video so you can have a chance to put it in your calculator so you can see that for yourself. Now ask yourself, if you were to fold it over just over the x-axis, is it on top of itself? No. Likewise, if you were folded over just the y, is it on top of itself? No. So it's not symmetric to the x-axis or the y-axis, but, excuse me, can you flip it over both and it's on top of itself? And hopefully you agree, yep, if I were to flip it over maybe y first, I'm just going to kind of draw you a little jagged little dashed, right? If I flipped it over y-axis, then that top part there would be over here where I just drew those dotted points. And then if I were to flip it over the x-axis, all of those dotted points would be over the bottom piece here. And so sure enough, then this one is symmetric to the origin. So we'd say origin here. Origin only, okay? Scooting over to example 2, we would pop this in our calculator, but hopefully you've got a little bit of working knowledge of what this would look like. Y equals x squared plus 4. So x squared we know is our parabola. That positive 4 is going to shift us up 4 units. So should look something like that. Which axis could I flip that over and it would be directly on top of itself? Hopefully you agree, the y-axis. Right? If I flipped it over this y-axis, then everything would be on top of that left-hand side, or vice versa. Okay. Example 3 is not already solved for y. You might know what that is if you recognize what this equation is without having to solve for y. Certainly go for it. I'm going to first solve for y and talk about how to graph it in your calculator, and then I'll come back and say, hey, yep, this sure enough was. All right, so if, I want to solve for y, so I'm going to pull my x squared over, so I would get this off a smaller pen. Subtract x squared. So I would have y squared equals negative x squared plus 9. Last step, I need to get y by itself, so take the square root of both sides. So y equals plus and minus square root negative x squared plus 9. Now, you don't have a plus or minus button in your calculator, so what needs to happen then in your calculator is that you will go to y1 and you'll put in the positive square root of negative x squared plus 9. And then you'll go to y2 and you'll put in negative square root of negative x squared plus 9. And then you'll hit graph. And whenever you hit graph, Zoom 6, by the way, is always a nice window. But I believe, which Zoom is it? The Zoom 5 on this one, because it's a circle, if you hit Zoom 5, it'll look more like a circle in the window as opposed to Zoom 6. So this should be a circle centered at the origin with a radius of 3. 2, 3, 1, 2, 3. I don't know how well mine's going to look here, but I'm going to try my best. I'll go back and there we go. All right, so if we kind of ignore that little guy right there, that first little, there we go. That's not too bad. All right, so is this graph symmetric to the x-axis? Yes, it is. Is this graph symmetric to the y-axis? Yep, I can fold it over the y-axis and it's on top of each other. Can I fold it over both and it's still on top of each other? Absolutely. So I am symmetric to the x-axis, the y-axis, as well as the origin. Okay? All right, so let's move on into closing up this set of notes here with our odd and even functions. All right, there are tests here with these, and we will need to utilize these tests if you aren't given a graph. All right, so if you're symmetric to the y-axis, your function is known to be even. And I will say this: odd and even functions pop up quite a bit in trig and from time to time in calculus. For those of you moving on. All right, so if a function happens to be symmetric to the y-axis, you automatically know then that the function's even. There is an algebraic test, and like I said, we will be doing the test on these. We need to know this test. So the test is f of negative x. If f of negative x equals the original, you plug in, everywhere you see an x, you plug in negative x, you clean it up, and it equals the original problem, then your function is even. So when you're doing this, all signs are going to stay the same. All right, again, that's going to make more sense in just a moment, so hang with me for a minute. If a function happens to be symmetric to the origin, your function is odd. So to put that together, origin odd, keep those O's together. So if you're symmetric to the origin, you're automatically odd. The test here, you're always finding f of negative x. But if that f of negative x equals -1 times your function, so -1 times the function, then what that means then is that all the signs are going to change. All signs change. So if you look at from the original to your new function and all the signs change, that means then that we're odd. Okay. I came down here below and I said you are always going to find f of negative x. If all the signs stay the same, your function is even. If all the signs change, your function is odd. If there's a mixture of some staying the same and some changing, your function is neither odd nor even. But we do have to be careful when our function has variables in the numerator and the denominator, okay? And I'm gonna demonstrate an example of that on the next page for you, okay? All right, so now let's come on down below here and let's look at these first two examples where I just give you a graph. So looking at the graph over here on the left, what kind of symmetry do you have here? This graph is symmetric to which axis? Hopefully you agree, it's symmetric to the y-axis. And so if we're symmetric to the y-axis, we are even. Okay, so we're good to go there. And I didn't give you the function, so that was the sole way you had to be able to determine that this function was even. All right, moving over here to the right, example 2. What kind of symmetry do we have here? This time we are symmetric to which axis? Hopefully you agree, I'm symmetric to the x-axis. And so therefore, if I'm symmetric to the x-axis, I only have odd and even to choose from. Even symmetric to the y, odd symmetric to the origin, so that means this one has to be neither odd nor even. Okay. Let's flip it on over. And in examples 3 through 6, we are looking at determining whether these examples are odd, even, or neither. Okay. So let's come down here below in example 3. For all of these, this is where I'm going to find my f of negative x. And let me just remind you, let me see if I can move this. There we go. That's what I wanted to do. There we go. All right, so now let me get back to my pens. All right, so let me just remind you, we're always going to find f of negative x. If your function is odd, you're symmetric to the origin, and all the signs are going to change. All signs change. If your function's even, you are symmetric to the y-axis, and all stay the same. All my signs stay the same. Neither, there's no symmetry, and I would just call here, it's a mixture of our signs changing. Mixture of sign changes. Okay. All right, so now let's come down here to number 3. I want to find, you always find f of negative x. Everywhere you see an x, plug in negative x. All right, so you take a negative and you raise it to an even power. It comes out positive or negative? Hopefully you agree. It comes out positive. Same thing back here. A negative raised to an even power comes out positive times that negative 2, so minus 2x squared. Compare it back to the original. All signs stayed the same, or they all changed, or is there a mixture? My x to the 4th are both positive, my 2x squareds are both negative. They all stayed the same, so that means then this function is even. If we were to graph it, we would see that it's symmetric to the y-axis. All right, let's come over to number 4. Let's find f of negative x. Everywhere I see an x, I'm plugging negative x. So 3 times negative x to the 5th minus 6 times negative x cubed minus negative x. All right, a negative raised to an odd power comes out positive or negative? We agree that would be negative. So negative times positive, so that would be negative 3x to the 5th. Negative raised to an odd power is going to come out negative times a negative, so positive 6x cubed. 2 negatives side by side turn into a positive. All right, compare it back to the original. what happened to all of your signs? They all changed. And so since they all changed, that means that this function is odd. All right, I encourage you, you try example 5 on your own. Maybe pause. I'm still gonna go ahead and do it since there's only 2 examples left. All right, so f of negative x. Everywhere I see an x, plug in negative x. Clean up, I get negative 3x minus 9. Compare it back to the original. So here you can see your 3x changed, but your 9 did not. So this would be what I refer to as a mixture. And so since it's a mixture, we would say then that this is neither odd nor even. Okay. Now we're coming down here to example 6. In example 6, I have variables in the numerator and denominator. So I need to be really careful down here. If all signs stay the same, then I'm still even, okay? But if there's a mixture, I need to be real careful. And like I said, I'm going to demonstrate that down here for you. So I'm going to first find f of negative x, because that's what we always find, f of negative x. So everywhere I see an x, plug in negative x. So up top, I got negative x. On the bottom, negative x squared plus 4. So now let's clean that up. That gives me then negative x over a negative raised to an even power. Comes out positive, so x squared plus 4. Now, if you go back and compare it back to the original, you might be apt to say, well, there's a mixture. Some changed and some didn't, so it's got to be neither. This is where I said, like I said, if you have variables in the numerator and denominator, we need to be careful. So remember your test. Your test for, let me just remind you, your test back on the previous page, your test for even said that f of negative x equaled the original problem. So it's definitely not even, okay, because I don't equal the original problem. So I'm definitely not even. The test for odd, though, said that when you find f of negative x, that's equal to negative f of x. So we found f of negative x. Think about whenever you have a numerator and denominator, whenever we multiply it by a coefficient, we only multiply the numerator. So remember, this negative f of x, this is like saying negative 1 times your function. So negative 1 times my original function was x over x squared plus 4. So think about this negative 1 out here. This is like negative 1 over 1. When you multiply 2 fractions, you multiply straight across. So that would give me negative x over x squared plus 4. So sure enough, here's f of negative x. This is negative f of x. They are the same, so that means this function is odd. Okay. Now, if I wasn't able to show that those two are the same, I wouldn't be odd either. I would just say neither. Okay. So it's like I said, when you have a quotient, a numerator and denominator, you want to go one step further and think about it in that manner. Okay. All right. That finishes up this section. Thanks a lot. Bye.